Okay, let's get this party kicked off. This is going to be the first lecture for Chem 106 at University of Alaska Anchorage, which is our second course in the sequence for general chemistry. And we're going to start with chapter 15, which is chemical kinetics. So one of the things I really enjoy about second semester general chemistry is we get to start making sense of all the things that we learned in first semester. First semester, reactions proceed or do not proceed. Things dissociate or do not dissociate. It's very black and white in terms of the way we're viewing reactions. And now that we're transitioning into second semester, what we get to see is that there's a shade of gray, continuous spectrum in reactions, where we're going to discuss how much reactions proceed and how quickly they proceed, and how we can manipulate those factors as part of the reaction down the road. So whereas 105 or first semester felt really jumbled, there's lots of things that seemingly are disconnected, and you're just grasping at information as quickly as it's thrown at you. This semester, there's a lot more cohesiveness to the way we view the curriculum, and we start to pull all of that together. So this is one of the more enjoyable classes for me to teach conceptually, and I think the students overwhelmingly really enjoy second semester as well. So with that as a little preface, let's go ahead and get kicked off here. If I can figure out how to change slides. Here we go. All right, so chemical kinetics. What are chemical kinetics? It's the study of the factors that affect the rate of chemical reaction. A good example of that would be temperature, for instance, and that's the one we're going to lean on the most out the gate. But it's really just an expression of reaction rate. So when we talk about reaction rate, it's interchangeable with kinetics. It's how fast is a reaction taking place. And another way to look at that is asking yourself, how fast is the reaction making the product of the reaction, or how fast are we consuming the reactants? Because those two are inextricably linked, right, on our molar ratios, which describe the reaction. So let's talk about that rate a little bit. Everyone, not everyone's had basic physics yet, but we have an intuition for what rate is. And it's really just quantifying change over a period of time. So everyone's comfortable with the concept of miles per hour being a rate, where we're looking at a magnitude of some effect over a given amount of time, typically in America, miles per hour. Unless you transition to Canada, and then you wonder why everyone's going 100. So let's take a look at it in terms of chemical reaction rate. To talk about chemical reaction rate, we're going to just be looking at the change of concentration, typically in moles per liter, over time. So remember, when we're looking at this equation, let's go ahead and start with the reaction. For the reaction in this example, we're going to look at hydrogen gas reacting with iodine gas to form two equivalents of hydrogen iodide gas. And now, remember, this is a 1 to 1 to 2 molar ratio, where both reactants have 1 mole equivalency and the product has 2 moles equivalency. So when we look at this rate, the easiest way to view it is to look at these delta signals here, right? So we're going to look at the negative change, delta being change, in the concentration of hydrogen gas over a unit of time. And if we wanted to quantify this, if we had two data points and we were interested in looking at the average rate of change over time, what we would do is we would take the concentration of the hydrogen gas at time point 2 minus the hydrogen gas concentration at time point 1, and then we would also look at the delta between time point 2 and time point 1. Now, I'm not a big fan, for those of you, actually none of you have had me for first semester chemistry, but I'm not a giant fan of the T2, T1 nomenclature. I prefer, when I'm looking at delta, to think of things as final minus initial. So whenever I see delta, I think final minus initial. So whenever I see T2 like this, I'm thinking concentration of hydrogen gas at my final time point minus the concentration of hydrogen gas at my initial time point. And that's how I'm going to be viewing this. So when I'm describing these reactions, I'm probably going to defer to final minus initial because it's a lot easier to conceptualize where you end up and where you start as part of this process than thinking numerically 2 and 1s. So that's my preference. If you think of 2 and 1s and that works for you and that's the way you learned it last semester, there's absolutely no problem with that whatsoever. So what's this look like if we're actually evaluating the change of concentrations? Well, let's take a look at this graph. And if you look along the y-axis, you can see here we have concentration in moles per liter or molarity. And on the x-axis, we have times in seconds. And we're looking at the same reaction. 1 mole of hydrogen gas reacts with 1 mole of iodine gas to form 2 moles of hydrogen iodide gas. And what we'll see right away, let's take a look at the green line. You can see the green line is an expression of the concentration of hydrogen gas. And because it's the reactant, as the reaction proceeds, it's being consumed, and we would expect, and we see, the concentration of the hydrogen gas decreasing over time in a nonlinear fashion. Now, as the reaction proceeds, the product we expect to accumulate go from nothing initially to whatever our final concentration is, and you're going to see that proceeding on the red line. You'll also notice the rates of reaction are different because for every mole of hydrogen gas which is consumed, we're making 2 moles of hydrogen iodine gas. This makes sense. So we would expect the rate at which hydrogen iodide increases to be greater than the rate of decrease for hydrogen gas. And we see this effect if we look at this dashed line here. That's the time point around 50 seconds. And, or does it say 4? No, that's about 50 seconds. And if we look at the instantaneous rate at that point, or we could call it the average rate over a 40-second period, you see that 0.56 moles have been consumed, 0.56 moles of hydrogen iodine gas have been produced, is the concentration, versus losing 0.28 moles per liter of the hydrogen gas. And that is exactly twice, so in terms of absolute values. Let's talk about that average rate thing a little bit more. So average rate is just looking at final minus initial over a period of time. And it's an approximation of a curve. So if I'm going to hop back here, the rate is actually always changing. So if we're looking at an average rate, we're just taking an approximation at any point along this timeline. If I come back here and we look at the average rate over different time intervals, starting, say, time at 0 seconds, and we have 10 seconds, 20 seconds, 30 seconds. Each of these are delta of 10-second intervals. And if we start with a concentration of hydrogen gas of 1 mole per liter, or 1 molarity, at 10 seconds, we see that we've got 0.819 mole per liter. At 20 seconds, we've got 0.67. At 30 seconds, 0.549. Now, the delta for each of these over these 10-second periods is shown right next to it. So we have negative 0.181, negative 0.149, negative 0.121. What you'll notice here right away is the change, the delta in the concentration over that 10-second period is decreasing with each interval. So the rate in per second, if we divide by, delta concentration here over delta time, is going to be the rate term, negative delta H2 over negative delta T. And you can see that that's going to be 0.0181, 0.0149, 0.0121, etc. And so over each 10-second interval, as the reaction proceeds, the average rate over that interval is decreasing. So these are averages. Now it's decreasing continuously. So if we were to look at this in even smaller intervals, like say 1 second intervals, it would be laborious, but you would see an even more accurate approximation of the instantaneous time as we shortened the interval. Now, instantaneous rate, if we were to shorten that interval progressively shorter and shorter and shorter and shorter until we were looking at a singular time point, that would be our instantaneous rate. And that is the slope at any point on a curve, or what we call a tangent line. So we can't really, we're not going to require anyone to do this, but if you have calculus, when you start to do calculus, you'll be looking at these, slopes at a point on curve. And that's called, a derivative or first derivative as a function of any kind of curve. So, to recap, as time goes on, rate of reaction generally slows down. And this makes sense because as the amount of reactants decrease, there's less probability of them colliding with each other because there's just not as many reactants because they're becoming products. And at some point, the reaction is going to stop, either because the reactants run out or because we're going to reach equilibrium. And we're not going to go too far into equilibrium yet because that's another chapter. But either a reaction will go to completion or you'll get a competing forward reaction and a competing reverse reaction, and those two rates of reaction will find an equilibrium based on the relative amounts of the reactants and products, and the reaction will cease to change in concentration, although you have continuous forward and reverse reaction. So let's take a look at reaction rate when it comes to stoichiometry. I've been emphasizing right out the gate this 1 to 1 to 2 ratio for our reactants to our product in this early example. And I really like this example because it has a little bit of stoichiometry included with it. So remember, the coefficients are not always the same for these reactions. And so if you don't have a coefficient in front, we're going to default to thinking this as a 1 to 1 to 2 ratio. So for every mole of hydrogen or every mole of iodine that's consumed, we're going to produce 2 moles of hydrogen iodine. We can also think of this as to make a single mole of hydrogen iodine, we need to consume half a mole of hydrogen gas or iodine gas. Now, because of that, the rate of change between the two is going to be different. We saw that in those varying rates of change in our slopes of our graphs a couple examples ago. So what we have to do is, in any type of rate expression, to be consistent, we multiply our rate expression by the inverse of the coefficient that we were looking at. So that sounds complex, but it's not really. It's just a correction for the number that's in front of our identifier. So here we have rate, and the rate in this case is a general expression where A and B are your reactants and C and D are your products. So you'd say whatever, let me see if I can just do a little thing here. A of A plus B of B is going to go to small c of C as a product plus small d of D. So, excuse my vertical handwriting on this tablet. So if we were to make any rate expression to transfer between reactants and products, the change in the concentration of A here is going to be adjusted for whatever the coefficient small a is. And then we can make that equivalent to whatever the change in the rate of C is based on a positive C. And both of the reactants have to have negatives because they're going to have negative changes of concentration because they're being consumed. And so to make them equivalent, we have to make a negative of negative to make them positive. And then remember, both of our products are going to remain positive because they're being produced, so the delta is always going to be positive. And recapping that, let's take a look at this figure again. We've got our hydrogen plus our iodine forming our two equivalents of hydrogen iodide. And our instantaneous rate at 50 seconds is going to be, let's see, for which one are we going to focus on? For hydrogen, here on our green line, is going to have a rate of 0.0070, and our rate of production of hydrogen iodide is going to be also with this expression 0.0070, because we are using our correction factor. Excellent. So, conceptual check-in 1. For the reaction, A plus 2B leads to the formation of product C, remembering that the coefficients for A and C are both 1 under a given set of conditions. The initial rate is 0.100 moles per liter per second. What is the change in the concentration of B per change in time under the same conditions? So this is where you can pause the video and check in. Are you looking at negative 0.05, negative 0.1, negative 0.2, or positive 0.2 moles per liter per second? Let's just kind of walk through this. I'll just let you pause it, but you can come back and we'll go back into the explanation here. And please do pause and give it a good shot here. Remember that B is going, let's see here, for the reaction rate, okay, what is the term for B under the same conditions? Now, B is going to be a reactant, therefore it will be becoming consumed, so its delta is going to be negative, so it's going to have a negative value. So right at the gate, we've eliminated D because it has to be a negative value. And because it has a coefficient of 2, we have to correct with a negative 1/2. So our correction factor is going to be negative 1/2 of 0.1 moles per liter per second. And I guess you guys can probably figure out that the correct answer is A because of that. And once you guys get into the habit of this, you're just going to run a couple problems in the homework. This is going to go super smooth for you. So how do we measure reaction rate? Well, to measure reaction rate, we need to actually physically measure concentrations of at least one of the components of a known reaction at a couple different time points. The book says many points in time. Many points is preferable to a couple, but we do need to be able to physically measure at least one of the reactants or the being consumed or the product being formed. Now, this typically involves having an instrument which has a probe which is continuously measuring, or pulling aliquots, meaning small samples from a reaction mixture as it's proceeding at known times. And the book goes into a couple different techniques for measuring chemical compounds, including polarimetry, spectroscopy, and looking at pressure for gaseous reactions. And I'm not going to lecture on those because we're not going to go into real depth with those tools. Please read that section of the book, but it's not going to be something I'm quizzing you on. I'm not going to ask you what the components of a gas spec are or an LCMS or anything like that right now. I want you to be aware of some of the names of the tools, get comfortable with some of the terminology, but I'm not going to ask you a question that makes you have to be an expert in quantitative chemistry yet. That's for later, and if you're a chemistry major. So, what are some of the factors that drive or affect reaction rate? First off, let's look at reactant concentrations. So, rate often depends on the concentration of one or more of the reactants. Now, that makes sense because and we're going to get to this in the next lecture. We're going to talk about how the more molecules there are in a given space, the more likely they're going to collide with the correct energy and orientation to cause a reaction. So it's just a matter of probability. If you have a higher concentration of reactants, they're going to collide more frequently with the appropriate energy and orientation to cause a reaction to proceed. Opposite of that, if you don't have that many reactants present in any given space, the odds of them reacting with each other are lower. So it's intuitive that a higher concentration of reactants is going to increase rate generally. Now, of course, the devil's in the details with that, but we're going to get there. So, of course, we have to have a way of describing rate, and that's going to be our rate law. So the rate law is an equation which relates the concentration of the reactants to the rate when, this is important, the reverse reaction is negligible. And that's one of the reasons when you see a lot of these problems in the homework, we're going to talk about initial rate of reaction, because there are no products at the very beginning of a reaction. It's all reactants, so the rate is going to be driven exclusively by the interaction of the reactants, and we don't have to worry about the reverse reaction of the product going back to reactants yet. Now remember, next chapter we'll get into equilibrium processes and all that's going to get turned on its head, but for now we can keep it simple and just look at the rate law in terms of the reverse reaction being negligible. So, rate law. The rate law of a reaction is directly proportional to the concentration of each reactant raised to a power. So for the reaction, reactant A goes to products, the rate law is just going to be this term. Rate equals K, and K is our rate constant, times the concentration of reactant A raised to the power n, which is called our order. And it's usually an integer which determines the dependence of the reactant on the concentration. And we'll talk about different orders, 0, first and second orders of reaction in a little bit. So, reaction order. The exponent on each reactant is the order with respect to that reactant. And the sum of all of the exponents of all the reactants is called the order of the reaction. So for this example here, rate, let's take a look at this one here. Rate equals the rate constant times the concentration of NO raised to the second power times the concentration of oxygen to the first power. The reaction is second order with respect to nitric oxide because it's raised to the second power, and it's first order with respect to oxygen, and it's third order overall because we just sum the second and first order for the two reactants in this reaction. So pretty straightforward. If you see something like this, you know right away if it's second order, first order, third order, and with what respect it's to second, first, and third order. So, a couple details. If a reaction is 0 order, meaning n is 0, the rate of reaction is always the same. Because when you raise something to 0 exponent, it's not going to be changing on you. So that means in this particular case that doubling the concentration of reactant A isn't going to affect the rate of reaction at all. It means when n is 0, it means that the concentration of the reactant doesn't matter for that particular reactant. If reaction's first order, the rate's always going to be directly proportional to the reaction concentration. So if n is 1, that means that if you double the concentration of A, you're going to double the reaction rate, because raised to the first order means that it's not being modified. Doubling is doubling is doubling in terms of rate because k is a constant. Now, if you reaction order second order, so if n equals 2, the rate is directly proportional to the square of the reactant concentration. So this really would mean that if n is 2, it means you're just squaring A. So the effect of A is squared. It's more than just proportional. And so if you were to double the concentration of A, in this particular case for second order reaction, you're going to be quadrupling the rate of reaction. It's going to have more than just a proportional effect. Once again, K is a constant, so it's unaffected by this term. So this is what it looks like graphically. If we have two different ways of looking at this here. If we look at our first graph, reactant concentration versus time on the left side, you can see on the y-axis we have reactant concentration, or concentration of A, over x-axis time in seconds. And then on the right side, we can look at rate versus concentration, and rate is going to be in moles per liter per second. On the y-axis and on the x-axis, we're going to be looking at the concentration of A. So let's see here. Just graphically, going back to the left side, if we're looking at the concentration of A versus time, zero order reaction where n equals 0, rate doesn't change when we change concentration. Notice the line is the same slope regardless, right? So this is, remember, slope is going to be an expression of change of A over change of time. So if we have a constant straight line like we do here, at any point in time that slope doesn't change. That means the rate of reaction does not change, which means we have a zero order reaction. If we have a first order reaction, it will change over time. And if we have a second order reaction, it will change over time with a greater effect due to the change in concentration of A. And really all we're seeing on the right side here, rate versus reaction concentration, is the same thing, but instead of having to look at the slope, we can just discuss it looking at the slope directly versus concentration change. And you can see that for zero order reactions, the rate of reaction doesn't change at all, regardless of the concentration. So it doesn't matter if the concentration is 0.2 or 0.4 or 0.6. At those places, the rate of reaction is the same. First order reactions are proportional and linear at those points where the relationship is the same between rate and concentration at all those points. But then it changes for second order because we're squaring the effect of the concentration on our rate. So let's go ahead and do a little check-in on our concept we just went through. So for a particular reaction in which A goes to products, a doubling of the concentration of A causes the reaction to double. What is the order of the reaction? Well, based on what we just talked about, everyone pause it, solve for yourself. And now that you're back, let's go ahead and go through the rationale, or see if you got it right, or see if you got stuck. So if you double the concentration of A, and it doubles the rate of reaction, what's the order? Well, we know that a zero order reaction has no effect on rate when you change the concentration. So it can't be zero order. And we know that a second order reaction, if you double the concentration, quadruples the rate of reaction. So the answer has to be 1, because it's a simply doubling the rate of reaction. Let's see if I'm right. Yes, we're right. Excellent. Still allowed to teach the class, thank goodness. So how do we determine order of reaction? Well, interestingly, the rate law has to be determined experimentally. You can't intuit rate law. we have to physically go into the laboratory and experimentally determine rate law. And the way we do this is we use the method of initial rates, where data from different experiments with different starting concentrations of reactants and the corresponding initial rates are given. So by varying the concentrations and looking at the rate of reactions, initial rate of reaction, we're able to ascertain graphically if that change of reactant concentration alters the reaction rate through a zero order, first order, or second order process. Now, if you have multiple reactants, you have to vary them one at a time to make this happen. So let's see here. Integrated rate laws. The rate law shows the relationship between rate and concentration. So it's useful to have these equations because it gives us the ability to have predictive power. Once we have these relationships, we can predict what's going to happen. We can look at change of one thing at one time point and intuit where it started. We can assess timelines for when a reaction began, if it was a nice slow reaction in environmental conditions. It gives us a lot of predictive power. So we like modeling things in chemistry as much as possible. And the book gives you a lot of solved algebraic equations, which are just derived on calculus. And once again, we're not going to be asking you guys to do any of that, but you do need to know the equations that we're using. So what we're going to move into here is the integrated rate law that shows the relationship between the concentration of reactant A and the time of reaction. How long has it been going on? So and these relationships vary depending on if it's first, second, or zero order. Keep that in mind because you're going to have to know quite a few equations off the top of your head. So for first order reactions, we have a relationship for our rate law, which is just rate equals K times the concentration of A. And because the exponent, or n, is 1, we can just let it drop because it's just 1. It's unaffected. Now, the integrated rate law for that, which gives us insight into the effect of time on this, is we look at the natural log of the concentration of A equals the negative K, or rate constant, times time, T, plus the natural log of the initial concentration of reactant A. And what's really handy about this relationship and the ability to model things is this conforms to the equation y equals mx plus b, our straight line equation, right? So here we have y negative mxb, where y is the, so if we were to graph this, or be solving for this, we'd have y as our natural log of concentration of A at time t. We have m, which is negative K, x, which is t, and b is going to be our initial concentration, the natural log of our initial concentration. And when we write the rate for this particular case, it's going to be molarity per second, or moles per liter per second. And K is going to have a value of s to the negative 1, or 1 over s. So because we can take this as a y equals mx plus b straight line plot, the plot of the natural log of the reactant concentration as a function of time should give us a straight line for these first order processes. So over here on the y-axis, we've got natural log of concentration reactant A at time t, and here we've got time t, and the slope of this line is minus k. So if you were looking to find the rate constant and you were given a couple different concentrations at different time points, you could plot those different concentrations at different time points, get the slope off of a linear plot of best fit, and then the negative of that would be your k, or your rate constant. Pretty slick. So let's check in on this concept. The reactant A goes to product B, has been experimentally determined to be second order. The initial rate is 0.0100 moles per liter per second at an initial concentration of A of 0.100 moles per liter. What is the initial rate of A? Oh wait, what is the initial rate at the concentration of A equals 0.500 moles per liter? And the answer should be, and this is a second order, right? So let's go and think through this real fast. If the initial rate's 0.0100 moles per liter per second at a concentration of A of 0.100 moles per liter, what's the initial rate at 0.500 moles per liter? This is going to be 0.250 moles per liter per second, or D, I believe. Yes. So if you got it right, congratulations. If you didn't, go back through and do another pass with that relationship. See if you can get it to work. All right, so let's take a look at a slightly more complex scenario, which is also more realistic. Determining the rate law when there are multiple reactants. Because so far we've been saying concentration of A goes to product. Well, that happens occasionally. But for the most part, we're having multiple reactants react with one another to form a product, unless it's a decomposition reaction. So changing each reactant is going to affect the overall rate of reaction. So what if we just doubled the concentration of A in this example here? What if we just double concentration of B? What if we double both? Will that affect the rate differently? Yes, it will. How do we describe that? Well, that's going to be the next little bit of information. To really quantify this, what you have to do is a controlled experiment where you alter one and hold the other constant so you can see the effect on rate, so you can determine whether the order is 0 first or second for A, 0 first or second for B. So you just have to hold your initial concentrations for one while changing the other. If you start changing both at the same time, you can do it, but it's more complicated than we want to make this class. And you'll notice that instead of using N for everything, they've added some different terms where M is just the reaction order with respect to A, and N is going to be the reaction order with respect to B. And that's just to keep those two different orders separate because they very well may be different. And this is just reviewing what I said. You have to determine the order of each reactant from experimental data, and once you know what M and N are with respect to A and B, you can determine the reaction order overall by summing them, where the overall order of reaction for this reactant would be M plus N. Oh, here's a nice easy one, a little concept check-in. This reaction was experimentally determined to be the first order with respect to oxygen and second order with respect to nitric oxide. or nitrogen monoxide. The diagrams shown here represent reaction mixtures in which the number of each type of molecule represents its relative initial concentration. Which mixture has the fastest initial rate? Well, if the reaction order for oxygen is first order, and the reaction rate for the NO is second order, that means that when you double oxygen's concentration, it only doubles the rate of reaction. But if you double the concentration of NO, you're quadrupling the rate of reaction. So because of that, having a higher concentration of NO relative to the oxygen is going to increase the rate of reaction more. Now, all these examples have the same total number of molecules of reactants, but the ratios are different. So what we're going to look for is the one which has the highest ratio of NO. And for clarity's sake, 2 reds is oxygen, and a red and a blue is a nitrogen and an oxygen. So I'm going to gravitate right towards C, where we have a 4:2 ratio of NO to oxygen. So that should be faster. It is. Excellent. Now that was first order reactions. Let's jump and take a look at second order reactions and then zero order reactions. Notice equations are different. So in this case, it's a second order reaction. Rate equals the rate constant K times the concentration of reactant A raised to the second power, because N equals 2. Now, if we want to have an expression which includes time, we're not going to be looking at the natural log anymore. We're going to be looking at the inverse. So instead of natural log of concentration of A at time t, for a y equals mx plus b, y equals mx plus b, nice linear graphical plot, which includes time. Y is going to be 1 over the concentration of A equals kT plus 1 over the concentration, initial concentration of A. So we can still ascertain K experimentally by looking at the slope of the relationship between the 1 over the concentration of A as Y and time being T. We also have a novel half-life term here, where T1/2 is 1 over K times the initial concentration of A. So, and also note that our rate term has changed as well. So this is exactly the same type of process as we did with the first order, but we have to have a slightly different equation to accomplish the same thing, to make a nice linear plot, but the process is identical, other than having a different equation. Note that at time equals 0, that's our initial concentration, which is what the naught means. And on the y-axis, we have 1 over the concentration of reactant A at time t, and on x-axis we have time t. Zero order reactions. Similar to before, but once again slightly different, where rate equals K times the concentration of A raised to the 0 power, which means in reality that the concentration of A doesn't matter at all, so we're going to pull it out of the equation, and rate equals our rate constant. It's a constant rate of reaction regardless of the concentration of A. So in this particular case, if we want to do a nice linear plot of this, we can go to this relationship here, concentration of A equals negative kT plus the initial concentration of A. So it's all about where do we start in terms of concentration, and then how long did it react at a constant rate of reaction K. And that's it. Gives us this nice plot. Y of concentration of A versus time. And slope is just minus K. Once again, different relationship to determine half-life of reaction. Different units for K. So half-life. Half-life is something that is kind of in everyone's vernacular because of decomposition of nuclear things, and all kinds of. Half-life is almost intuitive in the sense of what is half-life? It's the time required in a reaction for the concentration to fall to 1/2 of its initial value. So when you start a reaction, how long does it take to get half of the reactants consumed? And the half-life of the reaction depends on the order of the reaction, obviously, which is why we have different half-life relationships for first, second, and zero-order reactions, because they have different rates of reaction. But for a first-order reaction, let's look at that one first. So for a first-order reaction, if we have intuitively, let's see, time equals 0, we have an arbitrary concentration of 1.00 moles per liter at time 0. And if the time half-life is 100 seconds, then at 100 seconds we will have half the concentration being 0.5 moles per liter. If we give it another 100 seconds of reaction, it will have consumed another 50% of, if this was our new starting point, that amount, making the new concentration 0.25. If we gave it another 100 seconds, we would consume another half of it again, and that would be 0.125, and going on and on and on after 3 half-lives. So you can basically just have things in sequence to get to half-life, how many half-lives get to any particular concentration. Let's see here. This will be an easy one, I think, because it's just half-life. The images shown here depict the first order reaction of reactant A going to product B at various times during the reaction process. The black circles represent reactant A, and the red circles represent product B. What is the half-life of the reaction? Okay. Well, time 0 has, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units of reactant A. So at the half-life point, we'll have 5 black dots and 5 red dots. Let's see here. 1, 2, 3, 4, 5 black, 1, 2, 3, 4, 5 red. Should be 90 seconds. It's 90 seconds. All right. I think you guys are all going to be masters of this in no time. I'm going to skip this one. Shoot. Let's go back to it. A first order reaction, reactant A goes to product B, has a half-life of 25 minutes. If the initial concentration of A is 0.300 moles per liter, what is the concentration of B after 50 minutes? And you're not supposed to use a calculator for this problem because we want to keep it relatively intuitive. So, after 50 minutes of reaction time, if the half-life is 25 minutes, that means we'll have gone through exactly 2 half-lives, right? So and remember, if we're starting with 0.300 moles per liter of A, the question isn't how much A is left. The question is what is the concentration of product B? So it's a 1-to-1 ratio between A and B. We don't have to worry about stoichiometry. Or we do, I suppose, technically, but because it's 1-to-1 ratio, it's very easy to take into consideration. So if the initial concentration of A is 0.300 moles per liter, after 1 half-life, it'll be 0.150 moles per liter. And then after another half-life, it'll be 0.75 moles per liter. That means that the difference between the initial concentration, 0.300 moles per liter, and final 0.075 moles per liter is going to be 0.225. So our product, we should have 0.225 moles per liter of product B formed. And we do. Excellent. Here's a really nice little summary, and this is in the book. This is intro. Looking at a summary of our rate law, our units for K, our integrated rate law expression, what the straight line plot looks like, and our half-life expression. So this is everything we just talked about in a nutshell in one nice bit. You can take a snippet shot of this, use it as your note card, practice it, get it drilled in your head, because you need to know these things, guys. This is going to be essential for success on the Chapter 15 exam. Know this, practice using them, drill it until it's burned in your mind. So, summarizing basic relationships in kinetics. We have to experimentally determine reaction order and rate law. There's no way to intuit it based on the reaction. It has to be experimentally determined. The rate law relates the rate of the reaction to the concentration of the reactants using our term K, which is our constant, and our order, whether it's 0, first, or second order. And the integrated rate law, which is derived from the rate law mathematically, relates that concentration of the reactants to time, so we can figure out where we started with a reaction based on concentrations at a given time, or we can predict what a reaction concentration is based on initial reaction conditions. We can do both with that. Remember, the half-life is the time it takes for the concentration of the reaction to fall to 1/2 of its initial value. Remember that the half-life of a first-order reaction is independent of initial concentration, and half-lives of 0 and second order are dependent on initial concentration. And the final slide of this lecture, remember that we need to be able to do graphical determinations of rate law based on those linear plots. So a plot of concentration of A versus time, a plot of the natural log of A versus time, and a plot of the inverse of the concentration of A versus time allow us to determine whether or not a reaction is 0 order, first order, or second order experimentally. Because only the one of those transformations that gives us a straight line is going to be first, second, or 0, first, or second order. So if it's 0 order and you plot, saying this backwards. If you plot the concentration of A versus time with no transformation and it's linear, it's a 0 order reaction. If you plot the natural log transform of the concentration of reactant A versus time and it's linear, it's first order. And if you do inverse of the concentration of A, reactant A versus time, and it's linear, it's second order. And that is it for the first lecture. I'm going to pick this up, since we're mid-chapter, with the second in the sequence, and I'll be talking to you shortly again.